of the equilibrium constant. Okay? We can get this from tables using the formation gives free energies, or we can even use delta H's and delta S's in effectively the same way that we calculated delta S and delta H. Delta H became 1, delta S about a week ago. We can do the same type of calculations, summing over the reactants, summing over the products, and taking the difference between the product state and the reactant state. Ultimately, delta G0 represents the amount of work that the reactants can do versus the amount of work that the products can do. And when we take the difference between the reactants and products, we now represent the amount of, we're now calculating the amount of work that the reaction itself can do. Okay? It doesn't tell us about whether or not it's going to go or not. It just tells us the maximum amount of work that it could do at standard conditions. Right. Delta G0, that superscript 0, means standard conditions. Right. We'll talk a little bit more about standard conditions here in a second. But this is suggestive that there is a direct relationship between delta G0 and the equilibrium constant K. Right. And our job is to derive that. We already did it last time, but I think this explanation is going to make more sense. At least I hope so. I really don't like grabbing equations out of thin air and throwing them up over the board and saying, hey, here, trust me. And that's exactly what the textbook did. And that's kind of what I did on Wednesday. That's the reason why we're going back through this. Okay, so if delta G0 is small, if delta G0 is less than 0, that means we're going to have a relatively large K. In other words, equilibrium is going to favor products. The amount of work that can be possibly done by the reactants is much larger than the amount of work that can possibly be done by the products. You take products minus reactants, you're going to get a negative number. Okay? If delta G0 is greater than 0, then we have a small k, and our equilibrium is going to favor reactants. Now, as we showed on Monday, when we used the second law of thermodynamics and equated delta S for the universe to something going on in the system, we showed that delta G, not delta G0, but delta G is what predicts the spontaneity under any set of conditions. Okay, it does not have to just be standard conditions. All right, so delta G equal to 0, we have already said, was the condition for equilibrium. If delta G is less than 0, then the process is spontaneous. Specifically, it's spontaneous in the forward direction. In other words, if our process is a chemical reaction, delta G being less than 0 tells me the reaction is going to proceed forward towards products. Right. And the reaction is going to continue to move forward until delta G is equal to 0, until we reach equilibrium. That's what we've been talking about ever since we first started chapter 14. Reactions proceed until we reach equilibrium. We have the exact same result now, but now we have it in terms of delta G. Okay, if delta G is greater than 0, the process is non-spontaneous in the forward direction. If our process specifically is a chemical reaction, we can actually say the process is spontaneous in the reverse direction. Not the forward direction, the reverse direction. Meaning my reaction is going to move towards reactants until delta G is equal to 0. This is extremely suggestive of a relationship between delta G and the reaction quotient Q. All right. So delta G0 looks like it has a relationship with K. Delta G looks like it has a relationship with Q. And that turns out to be correct. Okay. We already know from chapter 14 that if Q is equal to K, we're at equilibrium. So the ratio of Q divided by K is equal to 1. Okay, we haven't looked at the ratios here, but if they're equal, then the ratio between the two of them has to be equal to 1, right? Right. So the condition for equilibrium is that delta G is equal to 0. Well, if I take the natural log of the ratio between Q and K, if Q over K is equal to 1, the natural log of 1 is equal to 0. Meaning, if I take the natural log of my Q over K relationship, I'm going to get the same result, at least the same numerical result, as the condition for equilibrium, which is delta G is equal to 0. Okay, this is suggestive right now that I have a relationship now between not only delta G, but the relationship between delta G and K, or Q, is actually natural log of Q over K. Let's see if that continues. If Q is less than K, means Q divided by K has to be less than 1. Q is smaller, I have a smaller numerator than the denominator, meaning I have to be less than 1. We already know what that means. If Q is too small, we have to proceed towards reactance in order to make sure that Q gets bigger so that Q approaches K. Correct? This is chapter 14 stuff. All right, well, what's the condition for delta G if we proceed towards reactance? Well, that condition is delta G has to be less than 0. What happens if I take the number of what happens if I take the natural log of a number that's less than 1? What do I get? 2. I get a negative. So I have two conditions that we already know. We already know about Q and K. We have two conditions now where the sign or the ratio of Q over K and taking the natural log of that gives us the same relationship with delta G. See if it works again, and it will. Q is greater than K, that means Q is too big. That means the products are too big. I need to shift towards reactance. The ratio of Q over K is going to be greater than 1. The condition for delta G, so that I shift back towards reactance, is that delta G has to be greater than 0. Well, if I take the natural log of a number that's greater than 1, I get a positive quantity. Okay, so I have this proportionality between delta G and the natural log of Q over K. Well, natural logs always give me a dimensionless quantity. They have to. I can't take a logarithm of a unit. Meaning, I'm going to need a proportionality constant to take care of the units. Delta G has units of energy, specifically joules per mole. So I need something that's going to give me joules per mole. Well, that proportionality happens to be R times T. The thermodynamical gas constant, 8.314 joule per mole per Kelvin. Multiply it times the temperature. That gives me joules per mole. Multiply that times the dimensionless quantity, which is the natural log of Q over K. And I have basically derived a relationship between QK and delta G. Okay. Now, if I have a quotient of log, if I have a log of a fraction, I can split that into the difference of two logarithms. And I get RT log Q minus RT log K. All right? Now, we derived that last time, but we derived it differently. And I thought there was a lot more hand waving than there is in this. I hope this makes more sense to you. Okay? So, starting with this, Q is always true. I can plug any concentrations or any pressures into Q, and it will be true. But K is only true at equilibrium. All right? So, delta G, if you want to think of it, it's a measure of how far my concentrations or my partial pressures are away from their equilibrium values. Okay? If Q and K are very different, the system is going to release or absorb an awful lot of free energy on its way to equilibrium. Since I'm really, really far away from equilibrium, what that means is the system is going to have to do an awful lot of work, or the surroundings are going to have to do an awful lot of work on the system in order for me to achieve equilibrium. All right? You have a rechargeable battery. You're hoping that delta G is very large so that it will last for a very long time. All right? What this means is that the magnitude of delta G itself is very large. All right? If Q and K are similar, that means I'm very close to equilibrium, and that means that my system doesn't need to do any work on the surroundings, and the surroundings don't need to do very much work on the system in order for me to reach equilibrium. I'm really close to equilibrium, so not much is going to change in terms of the Gibbs free energy. Delta G itself, the magnitude is relatively small. I'm fairly close to 0. I'm close to equilibrium at the beginning. Okay, so let's put these ideas together and look at a free energy diagram. This slide is identical from what you saw last time, but I hope it makes more sense now. Okay? So, delta G0 for a reaction is the difference between the delta G zeros of formation for all of my reactants and all of my products. Basically, how much work did the universe have to do to assemble all of the particles, all of the molecules that make up my reactants? How much work did the universe have to do to assemble all of the reactants and all the particles and all of the molecules of my products? Right? That gives me delta G0 for the reactants, that gives me delta G0 for the products. I take the difference, my final state minus my initial state. Final minus initial, I'm subtracting a larger number, delta G is going to be negative. Because of the way this curve is drawn, because this side is higher than this side, my equilibrium is going to lie on the product side of the extended reaction. The extended reaction just is basically 0 if I'm all products, and 1 if I'm 0 if I'm all reactants, and 1 if I'm all products. All right, so if it was half and half, basically delta G0 for the reaction was 0, then my equilibrium value would be right in the middle. All right, now this more or less shows a constant slope all the way from reactants until I get close to equilibrium. All right, the slope of the curve is delta G. It's just simply delta G. Delta G, I won't talk about that. We can define delta G a different way than what we have. I'm not going to do so. All right. Regardless, just like a ball rolling downhill, my reaction is going to find the bottom of the well. It's going to find the bottom of the slope. It's going to find the point where delta G, the slope, is 0. The slope is only 0 at the bottom. It's also the point that coincides with the minimum of delta G0 of the reaction. All right? So, the opposite for this would be a delta G0 being positive. The product delta G for formation is larger than delta G formation for the reactants. I have a positive. What happens there? I'm going to be favoring the reactant side of the extended reaction. All right. So, we get delta G0 from tables. Makes it easy to calculate. It does change with temperature. Lowest point is again the equilibrium. Delta G itself is really, we're writing it as a big delta. Mathematicians would hate us for this. Technically, it's the derivative of Gibbs free energy with respect to the extended reaction. Okay? Which would basically just be the slope of 1. But considers writing a derivative or defining a derivative as a symbol. We just write delta G for historical reasons and I think it confuses people. All right. And we can approach equilibrium from either side, exactly what we've already learned. Our Q can be too large, our Q can be too small. And so delta G is going to tell us the direction that a reaction needs to proceed in order to achieve equilibrium. But delta G0 tells us the position of the equilibrium constant. Okay? Based upon whether it's positive or negative. All right. Okay, so standard states. You need to make sure you understand the standard states in order to make sure that you know when you need to actually explicitly calculate delta G. Standard state, all pressures are 1 atmosphere, all concentrations are 1 molar. If I plug those in to any Q expression, since Q, big K and Q, always have concentrations or pressures, right? If all my concentrations are 1 molar, or if all my pressures are 1 atmosphere, Q must be 1. Okay? Also, by definition, delta G is equal to delta G0 when I have everything for standard when everything is in standard states. Okay, so I can plug that stuff in here. This is my delta G expression, but now I have substituted delta G0 in. Minus RT Q, log Q, but Q is equal to 1. Minus RT log K. Log of 1 is 0. I get delta G0 is equal to minus RT log K for standard conditions. This is where we started on Wednesday. And your book just throws this equation out there and says, hey, here you go. It doesn't try to explain to you where it comes from. I hope my explanation is a little bit better than what I gave you on Wednesday. Also, hope it's better than what the textbook has. Otherwise, I need to change the jobs. Okay? So, delta G is equal to RT log Q minus RT log K. I can plug this expression in for minus RT log K, and I now get delta G is equal to the standard free energy change plus RT log Q. Okay? Which, pretty much I'm ending where I started last time. I think the story is a little bit more complete, I hope. All right. So, last time I botched this problem, and I'm perfectly willing to admit that I made a mistake. Actually, what I'm going to say here is I'm going to be completely totally honest with you. I did not missolve the problem. The problem was solved correctly. The problem was I interpreted the answer wrong. Okay. So the issue that we had was reconciling the difference between K and the two temperatures and what our intuition told us about the reaction itself. Okay, so I have 2 moles of dinitrogen oxide giving rise to 2 moles of nitrogen and 1 mole of oxygen. My delta H at 298 is minus 163 kilojoules per mole. Delta H being negative says that the system is losing energy in the form of heat. Okay? Constant pressure, enthalpy is equal to the heat that's the energy lost is heat. All right, so if I'm losing energy in the form of heat, if my system is losing energy in the form of heat, where do I write energy? Is it going to be a reactant or a product? A product. So I'm going to go ahead and write that down. N nor G, if I can stop. All right. So we have K at 2 different temperatures that we're going to calculate. Let's go ahead and predict. What does Le Chatelier's principle tell us should be the relationship between the two Ks? All right. We do this. I have Kp at 40 degrees C, and I have Kp at 25 degrees C, and I want to know what goes here, greater than, less than, or equal sign. In other words, when I increase the temperature by 15 degrees C, which direction does the equilibrium shift? Does it shift when I increase temperature? Does it shift towards reactants or towards products? Shifts towards reactants. If I'm shifting towards reactants, what does that tell me about Kp at 40 versus Kp at 25? Is Kp at 40 going to be smaller than, equal to, or greater than Kp at 25? It's going to be smaller. It should be if thermodynamics and equilibrium really do talk to one another and basically mean the same thing. So my answer should be that Kp at 40 is less than Kp at 25. All right? So we have 2 equations we're going to wind up using. Delta G0 for the reaction is equal to minus RT log of K, and delta G0 for the reaction is equal to delta H0 for the reaction minus T times delta S for the reaction. I'm given delta H and delta S for the reaction. I'm also given my temperatures. So I can calculate delta G for the reaction at 25 degrees C. I have delta H, which is minus 163 kilojoules per mole, minus my temperature. I'm going to go ahead and use 298 for the Kelvin temperature, times the enthalpy, which is 148 joules per mole per Kelvin. Okay. Working that out, I'm not going to bother showing all the steps because my calculation was actually right. I'm going to get minus 207.10 kilojoules per mole for my delta G reaction. Now, I need to calculate K at that temperature, so I'm going to solve this for K. Big K is going to be equal to e to the minus delta G0 for the reaction divided by RT. Minus and minus becomes a positive. This is going to be e to the positive 207.10. I'm going to go ahead and convert that to joules. Divided by 8.314 joule per mole per Kelvin times the temperature, which is 298 Kelvin. I get e to the plus 83.59, which means my K is equal to 2.0 times 10 to the 36. Okay? That's a huge value of K. 2.0 times 10 to the 36. Okay, well let's compare that to the Kp at 40. We're going to do the exact same calculations, we're just changing our temperature. Delta G0 for the reaction is delta H0 for the reaction minus T, delta S for the reaction. In Gen Chem, we are going to assume that delta H and delta S are temperature independent. Luckily, we don't have to integrate. Minus 163 kilojoules per mole, minus my temperature, 40 plus 273 is 313, times the same delta S, 148 joule per mole per Kelvin, and I get that delta G is equal to minus 209.32 kilojoules per mole. Okay? I plug that in for my K expression, e to the plus 209.32 times 10 to the third joules per mole, divided by 8.314 joule per mole per Kelvin times 313 Kelvin. I get e to the plus 80.4, which is going to be 8.6 times 10 to the 34. Kp is at 40 is 8.6 times 10 to the 34. Kp 25 is 2.0 times 10 to the 36, which is exactly what we predicted based upon the Le Chatelier's principle. Yes? Technically speaking, yes. For the purpose of this course, no. The temperature dependence of delta H and delta S for a reaction is very, very small. It does exist, but in order to do so, you have to do things like integrate against the integrate over the temperature-dependent specific heat of reactants and product. No, you don't integrate in Gen Chem. All right. It's not a calculus-based course. All right. If you really want to know, take PChem in the fall. All right. And then you recognize the fact that you're glad that we just treat it as a constant. So, again, Le Chatelier's principle, thermodynamics, they agree with one another. All right. So, let's switch gears. The last major topic we're going to discuss this semester is electrochemistry. And it kind of pulls everything that we've learned this semester together again to show us basically what are the number one ways that we use chemistry to generate, well, to do work for us. Whether it be in a cell phone or a laptop or, I don't know, plating metals on other metals, making a chrome bumper. It's actually going to take us, it will probably take us about 6 lectures to get through this stuff, and that's not counting today. All right. So it'll be 5 or 6, depending on how fast we go. It'll also depend on exactly how much nuclear chemistry we're going to have on exam 4. All right. So today I want to, well, your objective 9, which will be next to last, Alex assignment, will be due on the 22nd of this month, which is, let's see, this is the 10th. So, 2nd, 12 days. So a week from this coming Wednesday. 17 topics. That due date may change, but don't count it. Right? It may change. There will not necessarily be an assessment due afterwards, or actually there won't be one. So this is going to be the majority of the material that's going to be on the next exam. All right. So, I don't know if you've noticed this recurring theme in Gen Chem 2 or not. I hope you have. We're kind of revisiting the things that we covered in Gen Chem 1, and we're just treating them more mathematically. All right. Things are not as black and white as they were in Gen Chem 1. Now, okay, now there's fuzzy shades of gray in between, and all of a sudden we have to solve a KSP problem instead of just saying, hey, this is insoluble and we get a precipitation reaction. All right. So most of what we did in most of what we've been doing for the last month and a half has been revisiting Chapter 9, Reactions in Aqueous Solutions. Acid-base reactions. So there were proton transfer reactions. We spent 2 chapters. Well, the majority of 2 chapters, all of 16 and half of 17, treating acid-base reactions the way you should treat them. Okay? Precipitation reactions. The solubility rules, which we finally decided on the rules, there were just fuzzy guidelines. And we also revisited that in Chapter 17. So the main theme for this chapter is oxidation, well actually the entire theme for this chapter is oxidation reduction reactions. Okay, well, oxidation reduction reactions are nothing more than electron transfer reactions. We like to transfer protons and we like to transfer electrons. All right, and that's, well, what we're doing in this chapter. Okay, so some of this is review from what we did last semester in Gen Chem 1. So about the first section here may go a little bit quick. Oxidation reduction reaction, we also call it a redox reaction. Why? Because chemists are lazy. You're not going to call it ox-red, so we just call it redox. Right. Electron transfer reaction. Oxidation numbers change. I'm not going to explicitly reteach you how to determine oxidation numbers, but I will basically give you general guidelines now. Unlike formal charge, where the bonding electrons are equally shared between both atoms, oxidation numbers say that the more electronegative element gets all of the electrons in the bond. Okay? So instead of taking the number of electrons the atom brings to the party, minus the number of dots, minus the number of sticks, it's actually going to be minus 2 times the number of sticks. All right? Every bond will be attributed to the more electronegative element. We take electronegativity into consideration when we assign oxidation numbers. All right, oxidation is the loss of electrons. I hate memorization, so I use mnemonics whenever I can. I guess technically mnemonics are memorization. But this stuff, I mean, it's either one thing goes this way, one thing goes this way, and it's very difficult for me to remember it, personally. So I use mnemonics throughout this chapter. I was telling my wife last night, who is also a chemist, I don't like electrochemistry. Because I understand it, but to me it's one of the hardest subjects in Gen Chem. And she's like, why? It's so easy. Just moving electrons around. I know that, but I keep, yeah, anyway. All right. Reduction is the gain of electrons. So oxidation is the loss of electrons. Reduction is the gain. Oil rig, we're in Texas. Might as well make it in Texas theme mnemonic. There's a plethora of other mnemonics that you can use for oxidation reduction. Leo, the line goes Gur. Anybody ever heard that one before? Ah, a couple of hands. How about oil rig? Who's heard of oil rig before? Who hasn't had? Who heard it before? I taught you in Gen Chem 1. Okay. Anybody heard another mnemonic for oxidation reduction? There's only two. Okay. All right, now oxidation and reduction must occur together, like an acid-base reaction, which is a transfer of protons. They have to occur together because we're transferring electrons. Something has to give up the electron, something has to gain the electron. We can't have electrons just floating around in solution. All right? Ask a cloud what happens when they have too many electrons floating around. All right, anybody get woken up by thunder the other night? That's what happens when you get too many electrons in a cloud. Lightning. Last time I checked, we haven't had any lightning coming out of beakers in the lab. Okay, so oxidizing agent. If you're an agent, you're somebody who promotes something. All right, if you're a sports agent, you promote a sports star, or at least you hope they're going to become a star. That way you get rich by doing nothing but promoting a sports star. All right, an oxidizing agent promotes oxidation. It promotes oxidation by being easily reduced. Okay? Oxidizing agent is going to be the electron acceptor. Bunch of consonants. Oxidizing agent accepts electrons. Sorry, bunch of vowels together. It gets reduced. A reducing agent is going to be my electron donor. All right? It is going to be oxidized. It promotes reduction by being easily oxidized. All right, so the whole reason why redox reactions happen is because different elements have different tendencies to gain and lose electrons. Hey, we learned that already, right? Well, what? Electron affinity and ionization energy. Good grief. Periodic trends coming back in. That was what? Test 2 back in Gen Chem 1. Back again to rear its ugly head. Okay? So, when we put two things together in the same beaker, we know how to write the molecular equation for that. We have a blue solution here of copper sulfate. We put a zinc electrode in there, just a piece of zinc metal. And we know something's going to happen. Right? We know that as time progresses, the blue solution is going to turn clear, and the zinc metal is going to start to look like it's got a brown fuzz all over it. That brown fuzz actually happens to be copper. Now, molecular equations tell you what you go grab off the shelf in the lab. They don't tell you the chemistry taking place. For that, we need the net ionic equation. And there's the net ionic equation here. We're going to predominantly be dealing with net ionic equations in this chapter. Why? Because it gets rid of all the extra stuff. Sulfate's not doing anything. Sulfate's a spectator. It's there simply to balance charge. Okay, so we have the net ionic equation. What is being oxidized? What is losing electrons? Well, if it's losing electrons, it's going to be getting a more positive oxidation number. What's getting a more positive oxidation number? Zinc. Okay? So what's being reduced? Copper. Now, if you need to remember it this way, I am reducing my oxidation number from 2 plus to 0. It's being reduced. What about the oxidizing agent? What's the oxidizing agent? Again, copper. And then the reducing agent will be zinc. All right. Finally, we need to know how to write these things as half reactions. Okay, so in half reactions, we're going to separate, in terms of the reaction, we're going to separate the oxidation from the reduction. Okay, so my oxidation half reaction, zinc 2 plus plus 2 electrons. I go ahead and balance the charge. We learned how to do this last semester. All right, and then copper 2 plus 2 electrons to give me copper solid. You can see directly here in terms of the half reactions, zinc is donating 2 electrons to copper, and copper is accepting those 2 electrons. All right, now, that was balancing redox reactions back in Gen Chem 1. Alright, so that's balancing a simple redox reaction. They have to be balanced with respect to mass and charge. So we're going to practice. Right? And what I'm going to do is I'm going to practice balancing a simple one, but I'm going to practice balancing a simple one using all the rules that we're going to use for balancing a complicated redox reaction. Okay? So I have aluminum plus copper to give me aluminum 3 plus, sorry, aluminum plus copper 2 plus to give me aluminum 3 plus copper. Okay? Basically the same reaction as I had last time, except we're replacing zinc with aluminum, mainly because, well, this is going to be a 2 electron and 3 electron process. Okay, so step 1. And I have a handout for my lab students that I'm going to post for you guys on e-learning that contains these steps for balancing redox reactions. The steps in the textbook suck. I'm sorry, I'm not going to sugarcoat it. It's horrible. It gives you 2 sets of rules, whether you're dealing with acidic or basic environment. I think it's ludicrous. It's complicated. My rules, I think, personally, are simpler. And so I have a handout for you, and basically it's just the same steps that I have written up here. Okay? So if you really want to learn how to do it, you can use either way. It doesn't matter as long as you get the right answer. Okay? Again, I don't care how you show your work. You need to get the right answer. I think my way is easier. Look at the textbook, see what you think. I bet you agree with me. Okay? And I have 1 set of rules for 1 set of instructions for balancing in acid or in base environment, whereas your textbook uses 2 separate sets of rules. Doesn't make sense. So, step 1, assign oxidation numbers to all atoms and identify the substances being oxidized and reduced. Well, oxidation numbers. If I have something in its elemental state, then it has an oxidation number of 0. Otherwise, it's whatever that species, if I have a charged species, the oxidation number is that charge. So this is aluminum 0, this is aluminum 3 plus, this is copper 2 plus, this is copper 0. Not too difficult. Okay? So I've got all my oxidation numbers already taken care of. What's being oxidized? What's losing electrons? The aluminum. So aluminum is being oxidized, which means copper is being reduced. All right. Step 2 is to separate the reaction into my 2 half reactions, 1 for oxidation, 1 for reduction. Aluminum is being oxidized, so my oxidation half reaction is aluminum goes to aluminum 3 plus. Okay? My reduction half reaction is copper 2 plus goes to copper. Solid. Alright, that's step 1 and 2. Step 3. Balance each half reaction with respect to mass. Alright, now there are 3 steps here. Actually, technically there's 4. 1, balance all elements other than H and O. Okay. Oxidation, already balanced. Reduction, already balanced. Okay, this is not too hard. Balance O by adding water. Well, I don't have any O's. Balance H's by adding protons. I don't have any protons, I don't have any H's. Okay, this is not too hard. Step 4 here would be, if I'm in basic conditions, I have to add hydroxides to neutralize the protons. All right. We don't have anything here. This is kind of a boring one. But I just want to show you that the more complicated rules work for the simple redox reactions as well. Okay, step 4 is balance charge by adding electrons. All right, so I have aluminum going to aluminum 3 plus. All I can do to balance charge is add electrons. Okay? So I'm going to have to make sure that I'm careful there, that I get rid of any excess positive charge, or if I have excess negative charge on one side, I'm going to have to add more negative charge on the other side in order to get it balanced. I've got to pay attention to that. All right. So I add 3 electrons to the product side of aluminum. I'm going to add 2 electrons to the reactant side of copper. Step 4, make the number of electrons in each half reaction equal by finding the least common multiple. What's the least common multiple between 3 and 2? Least common multiple is 6, meaning I need to multiply my aluminum oxidation reaction by 2. And I multiply the copper half reaction by 3. All right. Remember that chemical equations are nothing more than algebraic equations. I can multiply, divide, I can do really whatever I want to as long as I can do the same thing to an algebraic equation. All right, so I multiply through by 2, multiply through by 3, and then I add them together. Okay, so 2 aluminums to give me 2 aluminum 3 pluses plus 6 electrons. 3 copper pluses plus 6 electrons to give me 3 coppers. I add them together and notice what happens. The number of electrons cancel. And when we get into more complicated things, more things will cancel other than just the number of electrons. But in this case, the number of electrons cancels, and my overall balanced redox reaction, 2 aluminum plus 3 copper 2 plus, give me 2 aluminum 3 plus 3 coppers. Last step, as is true for any and all balancing chemical equation type problem, check your work. There's absolutely no reason why you should ever miss a question about balancing chemical equations, because you can always check your work. Okay, you have to check to make sure that both charge and mass are balanced. Okay, so my balanced chemical equation, 2 aluminums, check. 3 coppers, check. 3 times 2 plus, I have plus 6 charge on my reactant side. 2 times 3 plus is a plus 6 on my product side. My charges and my balances are my charges and my masses are the same on both sides. I have a balanced chemical equation. Now, we can do that so much simpler by following the rules that you learned in Gen Chem 1. But what I wanted to show you is that the more complicated set of rules will work for any redox, including the simple ones. Basically, the big deal here is that because I didn't have anything else going on, all of my balancing with respect to mass first, all of those steps were just copy things down again. Okay? So, next time we will start with balancing not so simple redox. Thank you for your time and your attention.